Hi everyone, I am LJ Miranda, and I'm very excited to present our work, Hybrid Preferences, Learning to Route Instances for Human versus AI Feedback. So as a quick summary, in this work, we find that some preference instances are better annotated by humans than by language models. We then use that information to train a hybrid preference router that allocates instances to either humans or LMs. But first, I want to introduce what is preference data and why it is important. So, preference datasets are used for post training, specifically for aligning models to human objectives and values. So, a typical preference instance usually would contain a user request, then a set of model responses and their ranking. So, in this example, we have two responses labeled as the chosen and the rejected response. And the chosen response here is preferred because it correctly followed user instructions, which is to list down some interesting places to visit in Vienna. So once we have a set of preference instances, we can use them to train models using techniques like PPO, like in the RLHF setup, or as part of larger post-training pipelines, as seen in the 203 paper, where a preference dataset is used in algorithms like DPO, or direct preference optimization. So one of the main questions in our work is to identify who should annotate preferences. We can obtain preferences directly from human annotators. They tend to be high quality, but obtaining these annotations is quite expensive and also time consuming. An appealing alternative then is to synthesize preferences from large language models. They can be cheap and scalable, but they're also prone to biases and errors. So, the main point of our approach is to actually find the right combination of human and synthetic annotations. And we do this by identifying instances that are better suited to be annotated by humans. So, we introduce the hybrid preference router or Hyper. So, given a dataset without annotations, we pass it to Hyper and obtain a dataset with hybrid annotations from either humans and LMs. And then in practice, we use this annotated dataset to train reward models for RLHF. So, Hyper consists of two major parts. First, we train a performance prediction model or a PPM. So, this PPM predicts the performance of a reward model trained on a given preference dataset. So, in our case, we train a regressor using the features of the preference dataset and its reward bench performance or its reward bench score as target. For routing, we simulate different preference datasets with different combinations of human and LM annotations. And then once we have that, we use the performance prediction model to predict the performance of that reward model without actually training it. So we can simulate a lot of these candidates, get their performance, and then get the model or get the annotations of the model with the highest performance. So in order to train the performance prediction model, we first need to simulate different combinations of human and synthetic annotations. To do so, we constructed a new preference dataset called MultiPref, which contains parallel, human, and GPT-4 annotations. So here, we actually used MultiPref as the basis for generating candidates for training the PPM. So then each candidate is then described by a set of features. So for example, these features might include like the cosine similarity between model responses, the domain expertise needed to answer a query, or if that particular user query has a safety concern and more. Using these features allows Hyper to make routing decisions based on these groups of instances, and then also allows it to generalize to other datasets that share these features. So now that we have a set of features, the next step is to get the target. So for Hyper, we train reward models for each candidate and then measure their performance on RewardBench. So in practice, we collected 200 candidates and measured their reward bench performance. And then later on, we'll show that even with just 200 candidates, we can actually accurately predict RM performance, which is nice. So now that we have a set of features and that we have a set of targets, we then train a regressor to predict the performance of that reward model. So we trained several types of regressors and found that a quadratic regressor fits our candidates properly, which is also quite good. So during routing, if we want to route an unseen preference dataset, what we do is we first generate candidates with different combinations of human and LM annotations, and then we obtain their features. And then, since we have this trained PPM, we just use that to predict their reward bench performance. And then we find the configuration of the reward model or of that dataset with the highest predicted performance, and that becomes our hybrid preference dataset. And we use the combination of human and LM annotations for routing. So we route everything that was allocated to humans to human annotators and the rest for an LLM. So now for the results. First, we find that our performance prediction model is actually very reliable with decent RMSE when using a quadratic regressor. We tried testing different types of regressors here. We had linear regressor, we had light GPM, but at the end, using a quadratic regressor actually helps. In addition, during test time, we also find that simulating 1,024 candidates is actually quite enough to properly predict reward bench performance. Again, note this is during test time, so this doesn't involve training new reward models, and simulating new candidates is cheap. We also tested whether hyper generalizes across base models. So we tested on Quen and we also tested on Llama 3.1. And we find that our best hybrid mix outperforms pure human or pure synthetic annotations even if we change the best model for training RM. So this shows that our approach generalizes to any other base model in this case. Moreover, we also tested whether Hyper would generalize to unseen preference datasets. Throughout this presentation, we trained our reward models based on MultiPref, but we also wanted to ensure that training on MultiPref and having this performance prediction model will still work if we change the underlying preference dataset underneath. So here, we see that even if we train our PPM only on MultiPref, we find that our best hybrid mix, which in this case is the green star, is still effective in getting the best hybrid, best reward bench performance for different data sets with different data distributions. And note that HelpSteer, Chat Arena, Alpaca Farm, they have different ways of collecting human data. And this shows that our prediction model or Hyper itself can actually generalize to these different types of modalities or data sets with different distributions. And then finally, we also show that our hybrid mix results in models that perform well not only on reward bench but also on other evals. So for the past few slides, we've only been testing on reward bench, but we also wanted to show that even if we train on reward bench, or even if we use reward bench as our target, um, the preference router still generalizes to different types of benchmarks and evaluations. So in this graph, we show an aggregated score on GSM-8K, BBH, if eval, codex, and alpaca eval via best of n ranking, and find that in most cases, our hybrid mix actually still works. Furthermore, I think one thing that's very interesting about this work is that we show that one advantage of training the PPM as a regressor is that we can actually obtain fine-grained understanding of instances that benefit human annotations. In general, we find that instances that require subject expertise or with moderate safety concern actually benefit human annotations. We made several of these analyses, so feel free to check the paper out for more extensive analysis of these features. So, to summarize our contributions, we find that some preference instances are better suited to be annotated by humans than language models. We use this finding to build a routing framework for preference data, which we call Hyper, and that our routing framework is reliable and generalizes to different base models, benchmarks, and unseen preference datasets. Furthermore, we also obtained fine-grained understanding of what type of instances benefit human annotations. So this is the last slide. Finally, I'd like to thank my collaborators, especially Zheng Wang, my co-first author, and our supervisor, Pradeep Desigi, for making this project possible. I'd also like to thank all the folks from AI2, especially Yanai, Sachin, Valentina, Faiza, Noah, and Hannah, for their support and feedback. Again, feel free to download the full paper by scanning the QR code above, and thank you so much for listening.